We were dealing with alkenes and its reactions. Alkenes is the seat of nucleophilic center. It is electron rich as it is having both sigma electrons and pi electrons in the form of sigma bond and pi bond. This pi bond which is formed is in excess. The electrons are in excess. As it is electron rich, it can react with an electrophile. As there is no easy leaving group, the electrophile gets added up. That's why the alkenes can undergo electrophilic addition reaction. We have seen the halogen adds across the carbon-carbon double bond to give vicinal dihalides. It can also add up water across the carbon-carbon double bond. The hydrogen and OH group adds across the carbon-carbon double bond and it gives rise to corresponding alcohol. The water is added up across carbon-carbon double bond and that's why it is called as hydration of alkenes. This is an example for electrophilic hydration. The addition of electrophilic hydrogen from non-nucleophilic strong acid like sulfuric acid or phosphoric acid at appropriate temperature breaks the double bond present in the alkene and the hydrogen and OH gets added up across this carbon-carbon double bond and it gives rise to alcohols. As we have seen, one of the methods for preparation of alkanes is dehydration of alcohols. The alcohols I take, if I dehydrate, I'll get alkenes. If I hydrate, I'll get alcohols back. That's why it is reverse of dehydration of alcohols. If I take alkene and react with concentrated sulfuric acid as a catalyst with water and heat it, I'll get corresponding alcohol. The primary alcohols formation to form it requires high amount of energy. It should be heated at 170 degrees centigrade. For secondary alcohols formation, it should be heated at less than 100 degrees centigrade. For tertiary alcohols formation, it is more easy to form. It occurs at room temperature. How this reaction occurs? What is the role of concentrated sulfuric acid? As you know, it acts as a catalyst. How it catalyzes the reaction? If at all I do not add this concentrated sulfuric acid, reaction do not occur at all. With few drops of concentrated sulfuric acid, hydration of alcohol is possible. And what is the stereochemistry of addition? In case of halogenation, it underwent anti-addition. In case of electrophilic hydration, how it occurs? What is the intermediate form? In case of halogenation, it formed halonium as an intermediate. Let us look into all those things. That is, explanation of all this fact is the mechanism of the reaction. Addition of water. As I said, it is an electrophilic addition. Electrophile means it is electron deficient molecule or atom. It adds to it, which is the electrophile that is getting added up. Let us look into it. Sulfuric acid, which we use, H2SO4, it dissociates into H plus and HSO4 minus in the presence of water. This H plus and HSO4 minus, they are unstable. That's why to gain its stability, the H plus which is formed reacts with water molecule. The water contains oxygen and this oxygen is in sp3 hybrid form as we already seen. When it is present in sp3 hybrid form, it has two sets of lone pair of electrons. And this lone pair of electrons is in excess and that's why it is ready to give to the electrophile. H plus is electron deficient. That's why it can act as an electrophile. Excess electrons in the oxygen is shared with hydrogen. When this gets shared with hydrogen, what happens to oxygen? The electrons are taken away with H plus. That's why the oxygen become electron deficient. Hydronium ion is formed. This hydronium ion is also an electrophile. As it is electron deficient, it acts as an electrophilic molecule. This electrophilic molecule reacts with the alkene. I'll take ethene as a simplest example for alkene. This ethene, in the presence of hydronium ion, which is an electrophile, in the presence of the electrophile, there will be the disturbances of the electron distribution across the two carbons. As it is electrophilic in nature, when it comes in front of this carbon, this is electron deficient, the pi electrons moves towards the carbon which is facing towards the hydronium ion. As these electrons moves towards this carbon gains electron richness. As the electrons are pulled towards one carbon in the presence of electrophile, the other carbon which has lost the electron gains electron deficiency. One carbon is electron rich and another carbon is electron deficient. That's why it has induced polarization in this molecule temporarily. This temporary polarization that occur in the presence of an electrophile is called as electromeric effect. As we have already studied about the electromeric effect, the same electromeric effect what you have studied, it occurs in the molecule. The electron rich carbon, it is a carbon ion and this electron deficient carbon is a carbocation. And this won't stop over here. This electron rich carbon, the excess electrons, it shares with the H plus. How this H plus is formed? Hydronium ion is not stable as the oxygen here is electron deficient. To satisfy this electron deficiency in the oxygen, the carbon-hydrogen bond breaks and thus the electrons moves towards the oxygen and it becomes H2O. Once this takes these electrons back, the hydrogen which has lost the electron, it becomes electron deficient. This electron rich carbon, that is carbon ion, shares its electrons to electron deficient hydrogen. What I will get? An alkene with a carbon which is electron deficient. A carbocation is formed. This is the third step. that occurs in the hydration process of alkene. Then the nucleophilic attack occurs on this carbocation as it is highly unstable. As we know, the carbocations which are formed as the intermediate in the process of protonation of the alkene. As it is unstable, it is highly reactive. And as it is highly reactive and highly unstable, it is reacts with the water molecule. Oxygen is having lone pair of electrons. As these lone pair of electrons are shared with H plus, this excess electrons is shared with the C plus, CH2 plus to be precise. Once these electrons are shared with it, the OH2 attacks on this carbocation, and as the electrons are shared with electron deficient carbon, this oxygen becomes electron deficient, is also unstable. To satisfy this positive center on the oxygen hydrogen breaks bond, and this alcohol is formed along with the generation of H plus. Here this H plus which is added on to the water has got released. H plus which is formed during the dissolution of sulfuric acid has hastened up the reaction, and this has been released back, and this released H plus combines with HSO4 minus to get back H2SO4. The amount of sulfuric acid added can be recovered back. It hastens of the catalyst is the agent which hastens of the reaction, but it won't involve in the reaction. This is how the water addition takes place across the carbon-carbon double bond of the alkene. H plus is added first as an electrophile. Electrophilic attack takes place. In the next step, nucleophilic attack takes place by this H2O, and they'll get alcohol. The alkene has got converted into alcohol. The salient feature of this hydration of alkenes is that it follows Markovnikov's rule. It is also named as Markovnikov's. In some texts, they have mentioned as Markovnikov's. In some texts, they represent it as Markovnikov's. This rule was given by Markovnikov, the scientist, and that's why it is named after him as Markovnikov's rule. What is this Markovnikov's rule? He says this rule says that the hydrogen and OH adds across the carbon-carbon double bond in the process of addition. This hydrogen adds to the least substituted carbon. The Markovnikov's rule states that during the addition of water to the alkene, the hydrogen adds to the least substituted carbon. What is this least substituted carbon? R is equal to alkyl group. If R is CH3, CH3, CH double bond CH2 is propene. This carbon is attached to two hydrogens. This carbon is attached to one carbon and one hydrogen. This carbon which is attached to one carbon is more substituted. with carbons. This carbon is less substituted with carbon. The hydrogen adds to the least substituted carbon, that is this carbon, not to this carbon. H plus, in the presence of H plus, electrons moves towards this carbon. A carbon ion is generated and this adds onto this hydrogen and I'll get corresponding carbocation which is generated. As electrons are moved towards this carbon has got electron deficient. The OH minus attacks on the carbocation and I'll get corresponding alcohol. Why this hydrogen adds to the least substituted carbon? Why not onto the more substituted carbon? How it can be explained? Why is it so? Why can't it add on the carbon which is more substituted? Let us look into it and let us try to explain this. The carbon, in the presence carbon-carbon double bond, these electrons moves to one carbon in the presence of H plus and it can move to the least substituted carbon and this becomes electron rich. This electron rich carbon shares its electrons with H plus and it can give rise to this type of carbocation. Or the electrons can move towards the substituted carbon, more substituted carbon, and this gains the electrons. This electron rich carbon shares its electrons to H plus. Then it can give this intermediate which I represented as 2. This can move either to the least substituted carbon or to the more substituted carbon. Both varieties are possible. If H plus is nearer to this carbon, carbon ion is generated on this carbon. If this carbon is towards H plus, these electrons can move. As they are added in equal quantity, this H plus can be in front of this carbon or in front of this carbon. That's why attack at either this carbon or that carbon will be having equal chances. What type of carbocation is found when this electrons moves towards the least substituted carbon? You see here, this carbon is carbocation. This is substituted with one alkyl group. Here also another alkyl group. This is hydrogen. This carbon is attached to two carbons and one hydrogen. As the carbon is electron donor, it donates the electrons here also from these two carbons, that's it is more stable. This carbon which is attached to two carbons, it is called as secondary carbocation. This secondary carbocation is more stable. Why it is more stable? It is electron deficient. Carbocations are reaction intermediates. It is unstable. But as it is having two carbons which are electron donating in nature, it has positive inductive effect. It is something like I am electron deficient, I am having problem, but I have a wife who is working who can support me, and along with my wife my father-in-law also supports. Though I am electron deficient, because of the support of father-in-law and the wife, I become more stable. In this case, it is attached to two hydrogens and one carbon. I have the wife who can support me, but I don't have father-in-law. That's why though I am more unstable. This carbon cation which is attached to one carbon is primary carbocation. The carbocation which is attached to two carbons is secondary carbocation. Secondary carbocation is more stable than the primary carbocation. The one intermediate which forms in more quantity is the one which is more stable. Right? Here the secondary carbocation is more stable than primary carbocation. That's why this secondary carbocation is formed in more quantity, and hence the hydrogen adds to the electron, this carbon which is least substituted. The secondary carbocation it can be formed when hydrogen adds to the least substituted carbon. That's why this intermediate is formed preferably over this one. That's why I'll get always the secondary carbocation in 98% cases and 2% cases the primary carbocation. That's why hydrogen adds to the least substituted carbon as it forms the more stable intermediate, and hence this H and the OH attacks to the more substituted carbon, H attaches to the least substituted carbon. This is Markovnikov's rule. And why it follows Markovnikov's rule? To form the most stable carbocation, that is the reaction intermediate. If at all this hydrogen is replaced by another alkyl group, tertiary carbocation is there. That will be more stable. More stable the intermediate, more is the formation of that intermediate. That's why the one intermediate is formed more easily than two intermediate. This is the unique feature of the hydration of alkenes. We get the carbon to which hydrogen is attached to the least substituted carbon. Another salient feature of this addition of water across carbon-carbon double bond, that is alkene, is its stereochemistry. Let us look into it. This is not stereospecific reaction. It gives both the mixture of syn and anti-addition. Syn addition is 1 if the hydrogen and OH adds on the same side of carbon-carbon double bond. If it adds on the opposite side, it is called as anti-addition. You have seen syn addition in catalytic hydrogenation of alkenes. You have seen anti-addition in halogenation of alkenes. The two halogens are attached to the two carbons on the opposite side. It gives anti-product. In case of hydrogenation, the two hydrogens attaches onto the same side of the carbon-carbon double bond. In case of hydrogenation. In case of halogenation, it gives anti-addition product. Here, the hydrogenation of alkenes is stereospecific. It gives specifically addition takes place on the same side. Whereas halogenation is also stereospecific as addition takes place across the carbon-carbon double bond on the opposite side of the carbon-carbon double bond. That's why hydrogenation and halogenation are stereospecific reaction. Specifically, it forms one type of stereoisomer. Whereas the hydration of water is not stereospecific. It can undergo syn addition and also anti-addition. Why is it so? Let us look into it. Here, after hydrogen addition to the electron rich carbon, that is the lead substituted carbon, gives rise to carbocation. The carbocation is a reaction intermediate, and this is carbocation has planar configuration. The bond angle between these two is 120, here also 120 and here also 120, total it is 360. It can attack here also from the front side and also from the back side. If this is in the front side, if you can attack on the back side, it gives anti-product. If it is attacked from the front side, it gives syn product. Anti-product, opposite side, H and OH has attacked in the opposite side to give anti-product. It can attack on the same side of the where the hydrogen is attacked, and it gives syn, the H and OH added across the carbon-carbon bond on the same side. This gives syn product. As attack from this side, opposite side and the same side are having equal chances as the bond angle is 120 degrees. Hence, it gives two types of products. That's why it is not stereospecific reaction like that of hydrogenation or that of halogenation of alkenes. This is another salient features of addition of water, that is hydration of alkenes. In examination, they may ask a question, write the reaction involved in hydration of alkene, or write the hydration of alkenes. It may be a short answer type question. Another short type of question that can be asked is, write the salient features of hydration of alkene. One salient feature is it follows Markovnikov's rule. Another is it is not stereospecific reaction. Or a short answer type question can be asked like this: hydration of alkenes is not stereospecific. Explain. Another question can be asked as a give reason type of question, similar to like this: alkenes undergo hydration and it follows Markovnikov's rule. Explain. Another question can be asked like this: alkenes undergoes Markovnikov's addition in hydration of alkene. What is Markovnikov's rule? Explain. They may ask, write the mechanism involved in the hydration of alkenes. We have to write all the four steps, what we have shown already. That will be not a short answer, not a long answer. It is an intermediate type of question which can be asked for 5 marks. Write the reaction mechanism and the unique features of hydration of alkenes. It will be a 10 marks question or long answer type question. And accordingly, we have to write all the things from reaction to mechanism to unique features and explain those unique features. This is all about the hydration of alkenes. Let us look into other electrophilic addition reactions in the coming classes or the presentations.